Okay, so let's continue. So we just proceed, we continue with the proof that was begun before. Right, so we continue, and this over here is, in fact, the illustration for step 0 of the proof. You'll recall, step 0 was making certain geometric preparations. Right, and then step 1 was a process of constructing a certain auxiliary function. A certain auxiliary function. Right, and then there were certain cutoff functions that I had defined. So I'm not going to write them out. You all know what the meaning of chi1 and chi2 are, but let me indicate the supports. So this orange, the schematic in orange represents the boundary of a certain pseudoconvex open set that I have created that come from my hypothesis. So there was this neighborhood U on which, or at least on U intersect omega, there lives on U intersect an open set that I called W. You have a function that has a certain peaking behavior, right? So there were these two relatively compact open sets that I had defined. The smaller one I had called V1, and the larger one is V2, right? So this stuff in U is a neighborhood with certain geometric properties of its own, which were encoded in an earlier figure. You remember that? So as I had said, step 1, we need a certain proposition, right? Which I won't state. But I will just state the bare bones so as to give a quick sketch. So the proposition I had gives me the following estimate. So D is a bounded pseudoconvex domain, and then I have my data on D, which is a Q+1 form G, and I have that G squared times e to the minus phi dv. I am given that this is finite, and the estimate that I have is that there is a solution to the d-bar problem, which is denoted by u, so that u squared times e to the minus phi of z divided by 1 plus the Euclidean norm of z squared dv z, this is less than or equal to this thing here. So this u is, this solves the d-bar problem with the data g, right? Oh, and I keep forgetting the constant. So there is a constant which I said depends only on the size of D. And so a quick sketch of this. So here's a quick proof sketch, which I guess serves as a nice review for this whole method, right? So what we have here is I define my weight, psi. So I'm given this plurisubharmonic function phi, right? So I define C to be, well, the phi that you've been given plus 2 times log of 1 plus norm z whole squared, right? And then what we do is compute the Hessian. So that's a computation that everyone can do. I'll just leave you to check. So what I'm going to do now explains the role of this over here. So this is actually the weight in the basic theorem that I'm going to work with. So check that the Hessian, let's use a short form. So the Hessian form, the complex Hessian of C at the point Z applied to the vector V, well, this is greater than or equal to, remember, phi is already plurisubharmonic. So this is going to give me a non-zero contribution. So this dominates the Hessian of the function, so I'll put a 2 here, I suppose, 2 times the log of 1 plus dot z whole squared, right? And this actually turns out to be, this is just a basic calculation, it turns out to be this quantity, let me see, done this calculation by bare hands. Yeah, turns out to be, well, the norm, Euclidean norm of v squared divided by 1 plus the norm of z squared. So this is what comes up. And so this is just less than or equal to the norm of v whole squared. Times, well, 1 plus the diameter of d whole squared. So you must have been wondering about that funny condition I had about 0 being an omega closure. It's simply a convenience to be able to write this. Okay, that was the only reason why that was there. And in Debraj's parlance, this over here is that little c, that small quantity. So therefore, this implies, right by Hörmander, this implies that I'll have a 1 over c. So this therefore implies, well, I'll just say this. Right? No, there's one more little step that remains. So this is Hörmander. Which is that if I call this 1, it implies that the LHS of 1, well, is less than or equal to, so here is that 1 over little c in the parlance of the first week of lectures. So this is 1 plus the diameter of d squared. So this is typically would be a very large number. And then you'd have the integral over d of the square of the pointwise norm of the form g times, well, a priori, e to the minus phi divided by 1 plus mod z squared d vz, right? Except that, remember, g belonged to a certain L2 space, so there's a certain integral that is finite, so one can just use Cauchy-Schwarz. So this by Cauchy-Schwarz. Right, so you see, 1 over this is really, really innocuous, right? So by Cauchy-Schwarz, one gets the RHS of of the inequality 1, right? So that's a quick justification. Beg your pardon? Yes, thank you. Right, yeah. So we do need this. So there we have it. So this is the key theorem that I'm going to use. And I am now going to define the data that I require for solving a D-bar equation, okay? So let G of Z be defined as, so I'm going to use my holomorphic local peaking object as my initial datum. So I'm going to go with, I'll tell you in a moment, well, maybe not a moment, but tell you pretty soon why I'm going to go with this object. So this is a holomorphic object. This is a holomorphic function which, by definition, vanishes at the point P, which is 0. Without loss of generality, P is 0. And I'm going to extend this by 0. So I cut this off using the cutoff function chi2 that I defined last time. Notice chi2 smoothly drops down to 0 on the boundary of U. So you have this for all Z in U, and then I have 0 for all Z in omega star minus U. So I do want to point out, thanks to Debraj for pointing this out, those two cutoff functions I had written down, I had incorrectly said that they were compactly supported in omega star. But I did make that correction, so thanks for pointing that out. They are actually smooth, compactly supported functions on Cn, right? Beg your pardon? Yes, so, whoops, yes, thank you. Right, exactly. So this here is our data. And not actually U intersect omega, because this phi actually lives on a slightly larger object, right? So U intersect, it actually lives on U intersect, let's see, what was I need to look at my condition. It is conceivable that I might have stated the condition P, yeah, so this is actually, this is for all Z in W. And to make this data for the original D-bar problem, I'll say W intersect omega star. Okay, so this is my data, and define. So I'm now going to use the following notation, okay? So it's kind of annoying to have to use this schema of defining something and then redefining outside of the support of a compactly supported object, okay? So I'm going to use this notation. So if, let's see, well, if this shape over here, if this diamond denotes a function or a form, and let's say if this denotes a function or a form, then chi divided by G is this object that I just defined, is understood to be 0 outside the support of this object. Okay, so I'm going to seek a certain leeway in being non-rigorous about writing certain key objects. So now, so this is so let's apply the proposition I had stated last time. So today is the second, right? So let's apply the proposition of 108 to the following data. Omega is d bar of chi1 divided by g, where I am going to take my weight, phi of z, to be, say, kappa. I'm running out of constants. I've used k and I've used j earlier. So let's say kappa times the log of mod z, and I want kappa to be greater than or equal to 2n. This is the dimension of my real dimension of my ambient space. Okay, so the question is this legitimate? Right? This needs to satisfy a compatibility condition, right? So let's check. Let's check how these things are going to be, and probably we'll do it right on the diagram to save a little bit of writing time. So so we know that the form d bar of chi1. So remember, chi1 cuts outside of V2, right? So outside of V2, our form omega is 0 here. All right? And likewise, when you look at this region, so let me actually shade this. When you look at this region over here, this is a region where chi1 is the constant 1. So the numerator vanishes. So therefore, omega is 0 here. All right? And so I'm only left with this sort of an annular region. And let's analyze what happens in this annular region. So let's see what happens here. So let's look at d bar of omega. So, or rather, let's look at the d bar of this object. Let's look at d bar of chi1 divided by g. Now note, there is a reason why I have, let's see. Yeah. So note that there is a reason why I'm choosing this cutoff over here. This is a cutoff function that is identically 1 on V2, which means that on this annular region, G is a holomorphic function, and 1 over G is a holomorphic function because of the peaking behavior of phi. 1 minus phi is not going to be 0. So this thing is equal to, well, it is the d bar derivative annihilates holomorphics. So we just operate d bar past this guy, and you have d bar of chi1, which is equal to omega. Where is this? This is here in this annulus, right? Aha, see, so this is the d bar of some function. So omega, and it's just sort of zero everywhere else. So in fact, omega is, here are the two properties. Here are the two key properties. Omega is d bar exact, d bar closed. That it is d bar exact is the consequence of our theorem. So simple statement, d bar of omega is in fact identically zero on omega star. And let me also record this. Omega is C infinity smooth. Actually, for what I need, I just need to observe omega is continuous. But let's just state what we have. Omega is C infinity smooth. Okay. Right, so apply the proposition of which only the estimate survives to get okay, so I'm going to have to continue this on a different part of the blackboard. Let's do that. I guess I can erase this stuff. I'll just leave the estimate for a few moments more. Let's leave this up for a few moments more. Did I also say, I guess I should say, the choice of D over here is omega star. This is where I want to apply my estimate. So what do I get? So to get a solution U to the D bar problem, the problem D bar of U is equal to this chap over here, omega, right? Okay, such that, so please check that my choice of phi is plurisubharmonic, and so therefore we get the integral on omega star of norm u squared times, let's look at this thing now. I apply the exponential, and I am going to get mod z to the power kappa. Mod z to the power kappa, and of course I have some innocuous stuff. 1 plus norm z squared whole squared dv is less than or equal to the integral of over omega star of my form. This is omega squared, and then I simply have downstairs here norm z to the kappa dv z, right? And I keep forgetting the constant, so let me put that in. So this is all very faithful, right? Aha. So do you remember when Debraj had given his lecture where, having first proved an inequality of this form, well, essentially this inequality, with a C2 smooth plurisubharmonic weight. He had told us how, in fact, one doesn't need the weight to be C2 smooth. There is a way to finesse this. And Dror had made a very big deal about how singular weights are really, really useful. Remember that? Now, so please note, my P is actually out. So P is equal to 0 for today's discussion. This is out on the boundary, so that my weight doesn't need any mollification. It is nice. It is C2 smooth. But boy, it has a non-integrable singularity. This is why I chose kappa to be greater than or equal to 2n. This gives me a non-integrable singularity. So this is a non-integrable singularity. So this is kind of an instantiation of the point that Dror was making, and said this is a very big deal. It is definitely a very big deal. So you have this, but you see this, on the other hand, is finite. Because over here, my form is just dead on the water. It's 0. This is finite because omega is identically 0 near the point P, which I have, without loss of generality, taken to be the point 0. See that? So you see, this forces U to decay. All right? So then, let's write this down. So for some reason, that thing tells me I still have 55 minutes. That couldn't be right. I have half an hour to go. So therefore, because of these two, do you see this guy is finite, and unless I have this counteract this thing blowing up rapidly, I can't have this bound. So this forces, this means that the limit, as of now, I can only talk about approach to the point 0 of U of z equals 0. So this is my first point. Beg your pardon? Well, I guess I should probably, yeah, I'm waving my hands a little bit over here. Let's say we look at the limb soup of this object, which would certainly exist, right? And let's look at the lim inf of this object. So both of which will be measurable. So you can sandwich this integral between the relevant intervals. And the lim inf is going to still be dominated by this object. So at least we can assume that, oh, you know what? There's actually a lot simpler way to deal with this. So before I say this, there's a much simpler argument, although it uses some machinery. But since I need this argument, let me make this claim. Right, so I guess I'm appealing to one species of hard analysis or a different species of hard analysis. But the claim I'm going to make here is a claim that a version of which you've actually heard being mentioned during the first week of lectures. So my claim is, yeah, so probably I like this hard analysis argument. It's still a hard analysis argument. So my claim is that this U is C infinity smooth. C infinity smooth on on omega star. Okay? Now, if I get C infinity smooth on omega star, so I had already mentioned how one can control the lim-inf of this datum. Now, if I also have that this guy is C infinity smooth on the interior of omega, then I can also control the limp soup, which will again be a zero. So U is sandwiched to be sandwiched between its limp soup and its lim-inf as you approach zero. So now, I also want to, this is probably a nice Easter egg. This relies on the fact that my datum is a 0-1 form. So this is the caution you need to practice, okay? So you've probably heard so here is a sketch of this claim, sketch of proof. Sketch of the proof is that, first, you have actually been told, although probably they haven't seen the details of the Sobolev embedding argument, right? So by a Sobolev embedding argument, what do we have? We have that there exists some solution U tilde U d bar of U tilde equal to omega that is smooth. So Professor Stauber used the term in passing. This is the interior ellipticity. This is the interior ellipticity of d bar. Okay. So this is the best we can say in general. There exists some solution that is C infinity smooth. But I'm claiming that the solution that satisfies this estimate is also C infinity smooth. So now let's look at it this way. So we have that d bar of my solution minus this smooth solution is identically zero in the sense of distributions. Okay. But then I, in fact, repeat the gist of the Sobolev embedding argument once more. So the embedding argument applied to this. So so please note, this is some measurable function. So the Sobolev embedding argument gives that well. So the way to state this, the slogan is there are no fake holomorphic functions. If I have a measurable function that is annihilated in the sense of distributions by d bar, then it is forced to be holomorphic. So U minus U tilde is holomorphic in omega star, right? And beg your pardon? Even if it's exactly. So now this guy is C infinity smooth in omega star. This is a C infinity smooth solution. So all of this implies that U is C infinity smooth. Okay? So now we can easily control this thing, the limit infimum, as Z approaches via omega star to the point 0 of U of Z, right? Which is to say, I get 0. So I need to control the limit supremum of this. Okay, so there's a further bit of hard analysis that needs to be done, but it becomes a whole lot cleaner with this datum. So we can maybe not so easily control. This is due to the above claim. Due to this above claim, the limit supremum of that solution, and by control, I also show that the limit supremum is equal to 0. So sort of a sketchy explanation for what I was earlier calling statement number 2. So this is that the limit as Z approaches through omega star, the origin of U of Z, this is equal to 0. Okay, so let me now make 2 quick statements. And then I want to comment a little bit about the whole sort of geometric fiddle behind that picture. Okay? So this is number 2. So A, from 2, I can find a little epsilon such that mod of U of Z is, say, less than or equal to 1 for all Z in the ball with center 0, radius epsilon, intersect omega star. And B, now consider the compact. Consider the compact. I take omega closure, and then I punch out this tiny ball. So this thing here, this compact, sits properly inside omega star. You see that? So since U is C infinity smooth on omega star, on this compact, I have a bound from above. So these two imply that U of Z is less than or equal to the max of 1 and the supremum on K of K is this particular compact. Okay, so let's call this K. Supremum over K of the solution U. Right, and this is a finite object. So this is my point number 3. So you see, my domain of interest was actually omega. Now, given the problem that I'm interested in, I want pointwise bounds. I want a uniform bound on the values of U. Now, this is a pretty big deal because, for instance, there is an example by Sibony which shows he constructs a domain which is, in fact, C infinitely smoothly bounded except at one point, is, in fact, strictly Levy pseudoconvex at every boundary point except for one exceptional point. And such that there does not exist any bounded 0-1 form for which there is a bounded solution. So what I really need is a bounded solution. I am assuming very little about my omega except for a bunch of things around this point P, which I already said. Any known prescription for constructing peak functions requires one to do that first, right? Away from the point P, I'm giving myself nothing. The global control I have is given by having a Stein neighborhood basis, right? Now, of course, the global regularity of the Neumann operator N1 will, among other things, produce for me a solution. In fact, this is the solution that is orthogonal to the kernel of D bar. That is C infinity smooth up to the closure of omega. And if omega is bounded, then by compactness I get pointwise bounds. But see, this is an enormous overkill. This is a huge, huge overkill. But you know, that is the way things are. The slickest way that we know how to achieve this sort of a regularity result is through an analytical condition, which is the compactness of the Neumann operator. And we saw from Professor Stauber's lecture yesterday that in an ideal world, one would like a very simple condition. Simple, necessary, and sufficient condition, but even the specific case of a Hartog's domain in C2 shows us that things are subtler than one would initially suspect, right? So this whole existence of a Stein neighborhood basis is a geometric way of finessing certain difficulties, certain fundamental difficulties in obtaining uniform pointwise estimates. Even yesterday, I had mentioned that I could take out of the picture the conditions B and G, the Stein neighborhood basis condition and the first condition, and replace the two of these by some other condition, which would be a purely analytical condition. So this meta theorem is certainly not the last word, okay? But you probably now see the goal of working with this omega star here, okay? So things are kind of plain sailing from this point on. This was the hard part. Sure. Not really. Well, I guess I can construct, I can pick a choice of omega star, which is strictly pseudoconvex, except at the point P. But my initial conditions are such that I know that on this part of the boundary of omega star, with the exception of the point P, I am strictly Levy pseudoconvex. And I don't actually really care what happens further out. On omega star, yes. But there is still that one exceptional point. That's right. Exactly. Beg your pardon? So is there, simply because there is because of the characterization? Exactly. Exactly. Yes. Yes, yes. So if I had that, then certainly. But the fact of the matter is, since I only have the existence of a Stein neighborhood basis, I really don't know what happens. So you see, this part I do need to be strictly plurisubharmonic, because I need some positivity of the defining function of either this part or this part to do some surgery. So being strictly plurisubharmonic here is non-negotiable. And I really don't know what's going on farther out from here. So I do want to point out that the geometric fiddle is to get to this. And the reason I need this is because, remember, I need to get certain pointwise bounds on the function that I'm constructing, right? So that's why I need this. And I don't know, I might still need this picture. So I'm going to keep this picture up here. And I can lose this estimate too. So the upshot of all this is, so thus I can find a really large constant. There exists a really large constant, m star, positive, such that the real part of the solution that I had, u minus m, is greater than, or well, is less than 0. Well, I can achieve this on omega. I'm out of guesses on all of omega star, but this I certainly have. In fact, I have it on omega closure. Right? So therefore, so this is kind of the end of step 2. I'm going to define the following function. So first note that, so by construction, so let's call this 4. So by construction, this function minus chi1 of g plus u is holomorphic on omega star, right? Because what this picture tells you is that I have, u is a correction to this, and the del d bar of this is 0. And And this is actually the part that I need, which is because of this, chi1 over g plus u. So now, let me do the following. There's a way of writing this chi1 of g. Everyone is familiar with this. So I can write this as mod of g squared times minus chi1 times g conjugate. So now remember what g was. Inside the set where phi1 is defined, g is just 1 minus phi. So the real part of phi is positive because of the peaking condition. So the real part of this whole thing is strictly negative on omega. And let me give a name to this. Let me call this u star. This is my new u. So I'm actually going to put a u star over here, right? The constant is just eliminated by d bar. So you see, this whole thing has strictly negative real part, so it can never vanish on where? On omega. So the reciprocal of this is holomorphic on omega. See that? Now, okay, at this point I am ready to, this is the final step, so I'm ready to deal the knockout blow. This is constructing a global peak function. So the question that arises, why the hell did I take such this particular datum? I already had a peak function. Could I not have used the d-bar problem to find a correction that would have given me something holomorphic? Well, you see, the whole damn problem is that I also need to control the magnitude of the holomorphic function that arises out of applying the correction. And the way things work is sometimes writing down a correction multiplicatively as opposed to additively gives you a better sense of control. Because first of all, if the holomorphic object that I have is 0 where I want it to be, then multiplying something onto it is not going to change the value at that point. So as you can guess, this step will involve converting a 0 to a 1. So this step will involve taking an exponential. So those of you who have some experience with the multiplicative Poisson problem, this is where one takes cues from. I am, please note, not extending the given local peak object. What I'm doing is I'm modifying it slightly, which enables me a global extension with pointwise control. That's what's happening. And that is why the datum involves taking a ratio. Because, so remember, I took my phi and I converted it to a capital G with the property that G at 0 was 0. So anything that I multiply onto it is not going to mess that value up. So that's sort of a peg in the ground, Okay, so loosely speaking, that's the reason for, if you want to ask me, well, how do you know that you do it this way? This, what I just said in the last 2 minutes, is roughly the reason. Okay, so how much time do I have? Okay, so I might take a couple of minutes extra, okay, if you don't mind. Let us look at, so please note, so let's call this object, let's give this a name as well. Let's call this H, right? So here's one very simple statement, right? The sign of the real part of H is nothing but the sign of the real part of, well, this thing over here, minus chi1 divided by G plus U star. This is true, well, where this is in V2 intersect omega. V2 is where V2 is a set that contains the support of this guy. Okay? Now, well, this is kind of a simple observation, right? If you want to find the sign of the real part of some function, well, if you want to find the sign of the reciprocal, if you want to find the sign of the real part of the reciprocal of some function, you just need to look at the function itself, right? Because what you do is the reciprocal can be written as something with a non-negative denominator times a complex conjugate, right? So now, well, we've kind of done this, right? So let's look at the real part again. Let's look at the real part of H. So this is, well, minus, it is the negative of the real part of chi1 times G conjugate divided by mod G squared plus the real part of U star, right? Which I have ensured is negative, right? But now the great thing is, look, this is purely real. So this is just negative of the real part of G conjugate, which is the same as the negative of the real part of G, divided by mod G squared plus the real part of U star. And that is negative by construction because G, well, this is negative. Well, let me write this down. This is negative on V2 intersect omega. In fact, V2 intersect omega closure. Because, you see, G is 1 minus phi times something positive. Something positive, right, on V2 intersect omega closure. So here's something positive, put a minus sign there, right? So you have this. And outside of the support, so by construction, real part of H, well, so remember this notation? Outside of the support of chi1, this is all that survives, which by construction has negative real part. So the real part of H is in fact less than 0 on where? On omega closure minus V2, right? And then let's look at, so these are three quick statements, 1, 2, and 3. So now let us approach the point 0. If you approach the point 0, you have to go through the set V2, intersect omega. So note that, well, you'll have to compute the reciprocal over here. So this G is going to go onto the numerator. And you have stuff in the denominator whose real part we have established is strictly negative. So that part is going to be innocuous. This is the purpose of taking the reciprocal. As you approach the point 0, remember G is 1 minus phi. Phi is continuous up to the point P and takes value 1 there, right? So therefore the limit, in fact, I don't have to take a limit. This is defined at the point P. So h of 0 is equal to 0, right? And so we are done. So this implies that e to the minus, well, e to the h is a global peak function. See that? And we are done, right? So I'll not write anything. I'll just take half a minute more. I think I've gone exactly 2 minutes beyond my time. I had said that if I have the time, I will write down a condition, and it's again a geometric condition. It's something where you put your hands on the domain or the boundary of the domain given to you, and is sufficient to guarantee the existence of a Stein neighborhood basis. And so these are sort of quite tied up. You're mentioning a condition about the existence of a Stein neighborhood basis. Which way did the implication go? Property P1.
If you have P1,
right. Exactly. So there is sort of this companion universe, and the interesting question is which of the sufficient conditions implies the other? In other words, it would be interesting to see how much of a gap there is between one of the conditions and the other. And this in fact, is true about compactness of the Neumann operator and the Stein neighborhood basis condition as well. Or for that matter, I'm just talking about N1, compactness of N1 and the existence of Stein neighborhood bases. So there is a paper by Forness and Diedrich and Forness from the 1970s, which is about Stein neighborhood bases. And they provided purely geometrical condition, which is, again, we need a domain that's sufficiently smooth. I don't remember how much regularity the domain needs to have. And if the set of points at which the Levy form is not strictly positive definite can be stratified in a certain way, then that is sufficient to give us a Stein neighborhood basis, right? So this is the condition that I promised, saying that there are lots of smoothly bounded domains outside of the category of strongly pseudoconvex or strongly Levy pseudoconvex domains that do satisfy the Stein neighborhood basis condition, right? With those words, I stop right here. Thank you. Yeah. I believe, or was it either weakly regular or totally pseudoconvex? One of those two.
but I think his memory serves me right because of the stratification.
This is exactly the, yes. Does it depend on the hard part of Catlin's work or the easy part of Catlin's work? You can construct. Okay. Okay. Right. So this is the, yes. Yes. Right. Yes. So this is the part I was not sure about. So in yesterday's talk, do you remember I had mentioned that justifying the existence of a C infinity smooth solution right up to the closure? I hadn't mentioned why this is a big deal, but I had mentioned that any condition that gives me that gives me the control I need. And I wasn't sure whether this observation depended on the hard part or the easy part of Catlin's work. So I simply mentioned that there are other hypotheses possible, but it would take us out of the machinery of L2 estimates and would lead us to look at more PDE ideas on the Sobolev scale. But yes, I have heard of the result. I didn't know which part of Catlin's work it relies on.
I assume by the or
That's right, yes.
no, that's not.
Okay. Okay. So we have P1.